planet basketball is near the sun and is expanding at a constant rate, okay? That's it.
Wait, can you blow into it and it'll still work?
Yeah. We might have to shorten this part, right? Oh yeah, how's it gonna? Oh, we could just
Reinforce it.
I'm gonna just use scissors.
That works.
Reinforce it a little more, like on this side, in the inside. Just take this kind of right here. Yeah. You're terrible at taking it. Oh yeah. Now you just blow into it and spin it at the same time.
I need a bigger box.
Yeah, it's working.
Yeah. I feel like
It's perfect.
it actually works. Might not even need that.
I could have. Got it.
I want to kind of do like what he said, a bike pump, but like
Yeah,
in a
that's
way
good,
where you just
yeah.
bike pump and then it spins at the same time. Yeah, that's not gonna fall. But it's not gonna spin either.
You can make the hole bigger now though, so. You just put the problem like right there.
Oh, yeah.
Yeah.
Yeah. You have that on video now. You have that
Yeah.
on video.
For our related rates problem, we have a meteor smashing into a planet named Planet Basketball. This meteor causes the planet to shift its rotational orbit and become much closer to the sun. And as the planet gets closer and closer to the sun, its volume increases dramatically. So, what we're aiming to solve is the rate of change of the radius of the planet when the diameter is 4,000 miles if the volume of Planet Basketball is increasing at 376,991 miles cubed per second. So, the first thing we want to do when we start this problem is write down the formula for volume. The rate of the volume and the rate of the radius can both be solved for by using the formula for the volume of a sphere, which is what a planet is. So the volume for a sphere is 4/3 pi r cubed. Deriving this, we can find the formula to find the rate of change for a sphere. So we derive it in terms of volume and radius. So we have dv over dt is equal to 4 pi r squared times dr over dt. That is the derived form of the formula above. So when we plug in our numbers for dv over dt, which is shown in the problem to be 376,991 miles cubed per second. We don't have anything to plug in for 4 pi because those are coefficients, but we plug in for the radius r squared. Plug in for this radius, it's half the diameter, or 2,000 in this case. So 2,000 squared multiplied by the derivative of the radius, which is the rate of change of the radius. That's what we're solving for in this equation. So if we do some simple algebra, we can solve the problem to have dr over dt, or the rate of change of the radius, equal to 376,991 over 4 pi multiplied by 2,000 squared. The rate of change of the radius is changing at a rate of 0.0075 miles per second when the volume of the sphere is changing at 376,991 miles cubed per second. The second part of this problem asks if the volume is increasing at the rate previously given, how fast is the surface area increasing at. We use the same radius calculated in the problem before. We need to find, instead of volume this time, we need to use the equation of surface area. The equation of surface area is equal to 4 pi r squared, where r is the radius of the sphere. Once again, we can derive this to find the rate of change, and since we already have the rate of change of the radius, which is 0.0075, we can find the rate of change of the surface area. So once we derive surface area equation, which is 4 pi r squared into 8 pi r times dr dt is equal to ds over dt, or the change in surface area over time, we get to plug in for our variables. Ds over dt would equal 8 pi multiplied by 2000 multiplied by the rate of change of the radius over change in time, which is 0.0075. And that would equal 376.991 miles squared per second, which is the change in surface over time.